Jai Hind all students. So today again we are going to discuss the clipper circuit. This is the second session of the clippers. In the previous section we discussed about the series clipper. Today we are going to discuss about the parallel clipper. So we know that clipper circuits are those circuits which are having the ability to remove a certain portion of the AC input signal without distorting the remaining portion of the waveform. So basically we can divide these clipper circuits into the two sections, two categories, that is the series clipper and the parallel clipper. So we already discussed about the series clipper. Series clippers are those clippers where the diode is connected in series with the load resistance. So whenever your diode is connected in series with the load resistance, then such type of circuits are termed as the series clipper. These circuits can be biased clipper as well as unbiased circuit. Unbiased circuits are those circuits where we do not use any additional battery apart from the any input AC input signal. Whereas if you connect the apart from the diode and the resistance, if you do add the one more DC battery in the circuit, then we termed it as the biased clipper. So depending upon the diode direction, depending upon the battery, the amount of the voltage we are applying with the help of that battery, DC battery, how much of the input signal, what amount of the, which portion of the input signal will be removed and how much amount, that will be decided by the orientation of the diode and the DC voltage. So these are the various series clipper circuits which we have already discussed in the previous lecture or the previous session. Now moving on to the parallel clipper. So as the series clipper are divided into the biased clipper as well as unbiased clipper, positive clipper, negative clipper, in a similar fashion your parallel clipper are also divided into two categories, that is, it can be the positive clipper, it can be the negative clipper. It can remove the positive section of the input signal, it can also remove the negative section of the clipper. A complete positive can be removed with the help of your parallel clipper, or complete negative section can be removed, or a part of any input or the a part of the positive signal or the part of the negative signal, both can be removed. So if you are able to remove both the sections simultaneously, the positive half, the positive portion as well as the negative portion, then such type of clipper circuits are called as the combinational clipper. So this is the one simplest example of the parallel clipper circuit, which is an unbiased clipper. Here we can see that the no diode, no external batteries, DC batteries connected in the circuit. Also the diode is connected in parallel with the output voltage. So such type of clippers are termed as the parallel clipper. So during the positive half cycle, this is, let's say, this is 0 and this is, let's say, your time t1 and this is your time t2. So let's redraw this input signal here to analyze. This is our input signal Vi, this value is Vm, this is negative Vm, this is 0, this is T1 and here it is T2. So during the time period 0 to T1, whenever you are in the time period from 0 to T1, this terminal is at the positive potential and this terminal is at the negative potential. So this makes the diode forward bias, and when your diode is forward bias, and here we have considered this diode as the ideal diode. So the equivalent circuit would be, during the forward bias condition, the diode is forward bias. When your diode is forward bias, then it will offer you zero resistance. That means diode behaves as a short circuit. So if I draw the equivalent circuit, then this will be a short, and here we are applying the input voltage. So the output voltage will be equal to how much? The output voltage will be the voltage which will be the equal to the voltage across this load resistance, across this diode. And as this diode resistance is 0, so that the voltage will be equal to 0. So during the first positive half cycle, when your diode is in a forward bias state, your output will be equal to 0. Now coming to the negative half cycle, so T1 to T2 time period, so during the time period T1 to T2, this terminal will be at negative potential and this terminal will be at positive potential, and this positive makes your diode reverse bias. So when your diode is reverse biased, it will offer, because this is your ideal diode, and ideal diode will offer, during the reverse bias condition, it will offer the infinite resistance. So infinite resistance means diode is open circuit. So if I'll again redraw the equivalent circuit, then it will be like this. And the current, because it is open circuit, so current is 0, and if your current is 0, that means no drop will takes place across this resistor, so that your output will be equal to input. So if I draw the output waveform, if I draw the output waveform, so it will be 0 from 0 to T1 time period, and it is V input during the T1 to T2 time period. So this is how we can find out the output waveform of the unbiased parallel circuit. So let us take another example. Here in this example, we can see that one more component has been added in the circuit, and that is the battery. So first of all, at time t is equal to 0, when we are not applying any input signal, we will see that what will be the value of the, or what will be the condition of the diode. So we can see here that because the positive terminal of the battery is connected to the cathode of the diode, that means that will make your diode reverse bias, and this reverse bias, this diode will remain in the reverse bias position until the input voltage, exceeds the input this battery voltage. So whenever your input is less than V volt. If your V input if V input is less than this V volt, then your diode will be in a reverse bias state. And when your diode is in a reverse bias state, then it will be open circuit. And if the diode is open circuit, then your equivalent circuit would be this. So no current, current is, there is no closed path is available for the flow of the current. So the current will be 0 in this case, and if current is 0, then output will be equal to your input voltage. And this condition will remain until your input voltage is greater than or equal to greater than this V volts. So as soon as let's say this is your V volt. So as soon as your V input is greater than V volt, what happened? This is a positive voltage, and whereas this voltage is trying to make your diode reverse bias, because this is positive is connected to the cathode, whereas here we can see that positive is connected to the anode. So this input voltage will try to make your diode forward bias, whereas this battery will try to make your diode reverse bias. So whenever input voltage dominates your battery voltage, then diode will be in a forward bias state. So as soon as your diode will be forward bias, then the equivalent circuit will be this will be short and then connected to the battery, and here it is V0, this is your V input. So here if I write the KVL in this loop, then I can see that this is plus and minus, and if I write the KVL here, so V minus V0 is equal to 0. So output voltage will be equal to how much? V volt. Output voltage will be equal to V0. So we can say that if I draw the output waveform during the first half cycle, then during this time period 0 to, let's say, T1. 0 to T1, the condition is V input is less than this V volt, so that your diode is reverse bias. So the output will be equal to input signal. So here we are getting the output equal to input, and as soon as your input voltage exceeds this voltage, and this is what? This is our transition voltage. So in the previous lecture we have discussed about this term transition voltage. What is transition voltage? It is the voltage at which your diode transit from one state to the another. If it is initially, if it is in on state, and after this voltage it will go into off state, or vice versa. So this voltage will tell you that after this or below this your diode will be on state or will be in off state. So here you can say that here your diode is in off state. So, as your V input is greater than, in this section your V input is greater than this V volt and your diode is in off state. So, when it is in off state, then during the time period when V input is greater than this, then it will be in on state. So, if it is in on state, then it will be forward bias and your output will be equal to V volt. So, we can say that during the time period T1 to T2, your output will be equal to V volt. Again from T2 to T3, again our input voltage is less than your battery voltage. So, again we are in this state. So, we can say that 0 to T1 and T2 to T3, V input is less than V volt. So, diode is reverse biased or it is in off state, and during that period of time we are going to get the output voltage which will be equal to input voltage. So, this will be your waveform. So, this is 0, this is T1, T2 and T3. Now, during the negative half cycle, T3 to T4. So, during T3 to T4, your terminal, this terminal will be at negative potential and this terminal will be at positive potential. So, here this is interesting to note that now input signal as well as this battery both are making our diode reverse bias, because here the negative terminal is connected to the anode and also here the positive terminal of the battery is connected to the cathode. That means for entire T3 to T4, diode is in a reverse bias state. So, when if it is in a reverse bias state, it will be open circuit, this will be your equivalent circuit and output will be equal to input voltage. Output will be equal to input voltage. And what is your input voltage? This is your input voltage. So, here you can see that with the help of this circuit, we can remove this portion of the input signal. That means, what type of clipper is this? What type of clipper is this? This is a positive clipper, because positive biased clipper, because only a certain portion of the input signal, positive portion of the input signal has been removed with the help of this circuit. So, any query, any doubt about this? Anyone student having any doubt? Okay. So, coming to the next circuit, here the orientation of the diode is changed as well as the battery orientation is also changed. This is another form of the parallel clipper. So, again we will start our analysis. So, first of all we will see that initially what will be the condition of the diode. So, here you can see initially means when your input voltage is 0. So, initially when input signal is 0, we are at this position, then your diode will be in a reverse bias state. We can see clearly that anode of the diode is connected to the negative terminal of the battery, which will make your diode reverse bias. So, in that case, if your diode is in a reverse bias condition, it will be open, and when it will be closed for the entire positive half cycle, we can see very well that for complete positive half cycle, your diode is not going to be forward bias, because this positive terminal of the input signal is connected to the cathode of the diode. So, this is also making your diode reverse bias, and this negative terminal is also making your diode reverse bias. So I can say that for entire half cycle, that is 0 to T1. So for complete half cycle, complete positive half cycle, diode will be in a reverse bias state. So if your diode is in a reverse bias state, that means it will be open circuit, and if it is open circuit, then equivalent circuit would be, again this is your equivalent circuit, and here you are applying the input signal. So what will be our output? Open circuit means current is 0. If current is 0, no voltage drop takes place across this resistance. So output voltage will be equal to whatever input voltage we are applying. Now during the negative half cycle, let's say this is your terminal A and this is your terminal B. So during the negative half cycle, terminal A will be at negative potential and B will be at positive potential. I'll use a different color so that there will be no confusion. So I'll marking it as in red. So my terminal A will be at negative potential and B will be at positive potential. So this will try to make your diode forward bias, because now negative is connected to the cathode of the diode. But this is only possible when your input voltage V input, when V input is less than V volt, then diode remain in a reverse bias state. So output will be equal to input only. But as soon as your input voltage exceed this V volt, then diode will be in a forward bias state, and when diode will be forward bias state, then it will be replaced by and this equivalent circuit. This is minus and this is plus and V. So if I write the KVL in this loop, then what will be my KVL? It is minus V naught is equal to 0. So V naught will be equal to minus of V volt. So I may write, draw the output waveform together with the input waveform. So 0 to T1, during that entire positive half cycle, output will be equal to input. So you are going to get the same voltage, that is Vm. Now during the negative half cycle, when your V input, this is your transition voltage, this is your transition voltage of V volt. So during the time period T1 say T2, during this time period our diode is still in a reverse bias condition, because this voltage is in magnitude is less than the transition voltage. So diode is remain in the reverse bias condition, so output voltage will be equal to input voltage. So this is your input voltage, and as soon as yani up to this your diode is in a off state. But after this transition voltage, your diode comes in the forward bias state, and as soon as your diode comes in the forward bias state, then your output voltage will be equal to minus of V volt. So, it will be minus of V volt. So, T2 to T3 time period, during the time period T2 to T3, your diode is in a forward bias state and output will be equal to minus of Vm. Again, as soon as your input signal is less than, in magnitude, is less than this transition voltage, then again your device will be off. So, T3 to T4, again T3 to T4, again your diode is in a reverse bias state, output will be equal to input. So, this will be your output. So, 0, T1, T2, T3 and T4. So, in this circuit we can see that the negative, a portion of the negative half cycle has been removed with the help of this circuit. So, here you can see when your diode direction is this, then you are removing the negative portion, whereas in the previous case you can see when direction of the diode was like this, then we were removing the positive portion. So, we can conclude from these two examples that depending upon the orientation of the diode, we can remove either the positive half cycle or the negative half cycle. So, this is how we can design our own clipper circuit by using the various types of diode in the circuit. So, any questions so far? Any doubt which you are having? So, we can clarify here. It will be more interactive class if you guys will ask question in between. I will take up all your queries. You may write in chat box so that I can take up your problems. Okay. So, we have taken up this circuit so far, we have taken this circuit and we have taken this circuit. So, let us take another circuit. So, I am going to take now this circuit. Now, this time I will be taking, instead of taking ideal diode, let us solve this problem using the some practical diode like silicon diode. Okay. Okay, fine. So, let me take another circuit. Now, I am taking this as the silicon diode and here I am taking it as the 5-volt battery. This is some resistance, let me take it as 1 kilo ohm, and here we are applying the input signal. So I am taking it as 20 volts. This is 20 volt, this is minus 20 volts. So let us start analyzing this circuit. Initially, what will be the condition of the diode? Here we can see that this diode is forward biased by this 5 volt battery, but the diode will be, so you can say that during the first positive half cycle, your terminal A and this is your terminal B. So terminal A will be at positive potential and B will be at negative potential. So this will also make your diode forward bias. So I can say that during the time period 0 to T1, your diode will be in a forward bias state. So when your diode is in a forward bias state, so this will be the equivalent circuit will be of this. This is because this is your silicon diode, so it will be the barrier potential of the silicon diode is 0.7 volts. So that's why this diode will not be replaced by a short circuit like your ideal diode. Here you will be replace this diode by a battery of 0.7 volt, which is representing the barrier potential of that silicon diode. So that positive anode will be replaced by a positive terminal and cathode will be represented by the negative terminal, and this battery will be connected as it is. So this is minus and this is plus 5 volt and this is your 0.7 volt. This is V0 and here you are having your input signal with the polarity plus and minus. So now what will be your output voltage for entire positive half cycle? We'll write the KVL in this loop, because we know that in the parallel your voltage, output voltage means the two in parallel voltages are same. So whatever voltage is appearing across this will be appearing across the output voltage. So that we can calculate with the help of writing the KVL in the second loop. So I will write this minus of 5 volt plus 0.7 minus V0 is equal to 0. So V0 will be equal to how much? It will be minus of 4.3 volt. Now, as soon as you will enter in the negative half cycle, if you are in the negative half cycle, so this will be minus and this will be plus. Now, this negative battery is making your diode forward bias, whereas this negative voltage, input voltage, will try to make your diode reverse bias. And when it will be possible? Whenever your V input is greater than the minus of 4.3 volts. That means up to minus 4.3 volt your diode will remain in the reverse bias condition. Why now 4.3? Because 0.7 volt is required in order to overcome the barrier potential of this battery as well, and that's the reason instead of 5 volt here input voltage should be greater than 4.3 volts only. So your transition voltage will be minus 4.3 volt. So up to this voltage T1 to T2, because your input voltage is less than, your input voltage is less than this battery or this 4.3 volt. So, we can say that T1 to, during the time period T1 to T2, your input voltage is less than minus 4.3 volt. So, that your diode will be in a forward bias condition. Therefore, output will be equal to how much? It will be minus of 4.3 volt. So, if I draw so up to this T2 volt, what will be my output voltage? It will be minus of 4.3 volt. So, you can say that up to this voltage, your diode is in on state, and after this transition voltage, diode will go into the off state. So, you can say that during the time period T2 to T3, T2 to T3, your V input is greater than, V input is greater than in magnitude, we are talking about the magnitude. So, V input is greater than this transition voltage, so that your diode will be reverse bias. And if it is reverse bias, then the equivalent circuit would be this. And in that case, your output will be equal to input signal. So that up to after this will be your output. And again from T3 to T4, again your diode voltage is, input voltage is less than the transition voltage. So again your diode will be forward bias, and you will get the voltage that is equal to minus of 4.3. So this will be your output voltage. Any other, any question? Any question? Please students, please keep asking the question to get the maximum benefit of these online lectures. Okay. So far we have discussed the parallel clippers, which can either remove the positive half of the any input signal or the negative half of the any input signal. But what if you want to remove the both the portion of the input signal, means you want to remove a small portion of the input signal, also you want to remove a small portion of the, the positive portion also you want to remove, as well as you want to remove the negative portion also. So what is the answer? The answer is the parallel clipper using the two diodes in the different orientation, and that type of diodes are called as the combinational clipper. So here we have discussed, we are going to discuss one such type of circuit. Here you can see that one diode direction is like this and another is having the opposite direction. So let us study this circuit. This is very interesting, and if you understand the previous circuit, then it is very easy to handle. See, during the positive half cycle, let me mark this diode as D1 and this is D2, and one more thing I would like to add on in order to make you understand this this problem in a much better manner. I would like to take these values also. Let's take this V is 3 volts and V2 is, let me take it as 2 volt. Okay, and let me take this value as 20 volt, and this is also 20 volt, minus 20 volt of course. Now during the first entire positive half cycle, what is the condition? See, the diode D2, look at both the diodes one by one. First of all, I'll like to concentrate on this second diode. See, the diode D2, during positive half cycle, this terminal A at positive potential, B at negative potential, and so this positive will try to make your diode D2 reverse bias, because positive is connected to the cathode of the diode. So that this will make your diode. So this is clear that for entire positive half cycle, your input signal is going to make your diode reverse biased only. Also, the orientation of the battery shows that this also making your diode reverse bias. So I can conclude that for entire positive half cycle, my diode D2 will be in a reverse bias state, isn't it? It will never come in the forward bias state for the first positive half cycle. So it is as good as that you are not having this section during the positive half cycle. So in a simplified manner, what I can say? I can say that my circuit is reduced in this circuit, because this is the reverse bias, so this will be open circuit, so this will no more in the circuit. So this is, this is not my part of my interest during the first positive half cycle, isn't it? So now this is my circuit, reduced circuit. So this is a much simplified circuit now. We can very well handle this now. So during the positive half, this diode may come in the forward bias state, although this positive is making your diode reverse bias, but as soon as your input voltage is greater than this V1 volts, then your diode is going to be in a forward bias state. So what is your transition voltage? So your transition voltage would be how much? It will be 3 volts, V1 or 3 volts. So till the time your V input is greater than 3 volts, your diode will be in a reverse bias state. So when V input is less than 3 volts, then diode will be in a reverse bias state, and if it is in a reverse bias state, this will be open, and if it is open, then output will be equal to how much? That will be equal to input voltage. So I can say that during this time period, your output will be equal to input voltage only. Now as soon as, so I can say इस फ्रीज्ड हो गया है. Sorry, so we can say that during this time period your diode is in off state, and after that your diode may go into the on state. So as soon as your V input is greater than 3 volts, then diode will be forward bias, and when diode is forward bias, then it will be replaced by a short circuit. So output will be equal to 3 volts. So output will be equal to 3 volts. Again, when your diode is, so here your diode is in on state. again in this portion, again your diode is in a reverse bias state. So, output will be equal to input voltage. Output will be equal to input voltage. Similarly, for the negative half cycle, during the negative half cycle, this negative and this positive will make your diode D1 reverse bias. Only this will try to make your diode D2 forward bias, and that too after this voltage only. That means now I can say that during the negative half cycle, negative half cycle, our circuit will be reduced to this circuit only. Because for entire negative half cycle, this is going to be reverse biased. So, this is terminal A will be negative potential, because now we have entered into the negative half cycle, and this is positive, this is your V input. So, again let us analyze, and this is your V2, that is 2 volts. So, till the time, so this is your transition voltage, 2 volts. So, until and unless your V input is less than 2 volts, so diode will be in a reverse bias state. That means open circuit, so output will be equal to input. And as soon as your V input is greater than 2 volts, then this diode will be short circuit, and your output will be equal to, so minus 2 volt minus V naught is equal to 0. So, V naught will be equal to minus of 2 volts. So, here you can see that whenever your diode D2 is in reverse bias condition, output will be equal to input, and as soon as it is greater than this 2 volts battery in magnitude, then the output will be equal to the input voltage. So, here you can see this is your 2 volts and this is your 3 volts. So, here in this particular example, we have removed both the sections, the positive half, a portion of the positive half, as well as a portion of the negative half. So, both the portions has been removed by using a single circuit only. So, this is the combinational type of circuit, and this completes your yes, there is one question coming up, that why we use the clipper circuit. So, these circuits are termed as the limiter circuits also. So, here are the various examples, that whenever there are excessive noise or spikes are coming above certain level, you never would like to have any type of noise in your transmission. So, whenever you are having a certain amount of the noise is always always allowed, but after that you cannot allow after a certain level. So, that excessive noise, whenever there is excessive noise which is beyond a certain level, that can be limited with the help of these clipper type circuits. So, in FM transmitter we use the series type of clippers. Also, protection for the protection of the transistors from transients, means whenever you are using any circuit, so some type of noise, or you can say the atmospheric noise, they will be coming. So, and in order to protect your transistors from such type of noise or unwanted signals, we use these circuits. So here in such type of cases, we use the parallel type of clipper. We connect the parallel diode in parallel across these inductive loads, so that we can protect our transistor circuits. Okay, a frequently used half wave rectifier in power supply is a typical example of clipper. We already discussed about that, and it can also be used as a voltage limiter. Wave shaping के लिए भी use करते हैं, and sometimes these clipper circuits are more frequently used in the television transmitter and receiver circuits. So these are the few examples. I hope they will, I have taken your problem or you have taken your point. So this completes your clipper circuit. So very soon we will be coming up with the next topic, that is the clamper circuits. So I hope this will be very beneficial for my student, for our AKG students. So good day, bachcho. We'll see you soon. Thank you.